Right, yes. So co-workers and so on. I should just say that although I mentioned some high-performance computing facilities here, they were not necessary for this, for the examples shown here, where you can use a much smaller machine, as I've tried to extract some simplicity from a very large computer budget. So, yeah. So SiO masers in AGB stars, at least for the J equals 1 to 0, 2 to 1, maybe 3 to 2 in the lower vibrational states, they tend to form in these ring structures. Some examples here, there are different ways of representing these things. But the idea is that there's very rarely anything sort of right in the middle that's bright. Occasionally, yeah, there is, but as a rule, not much there. So can I place any geometrical constraints on what the shape of the objects that produce these rings can take? So going on, so the assumptions here are that the objects can be tracked in some observations over more than one cycle. So that favors a sort of bullet or cloud model over chance line alignments in the line of sight. So it's probably possible to ignore to some extent the overlaps of clouds. So I've used a model to get physical conditions from that corresponds to the brightest phase, which is around 0.2 in the optical scale, where the 43 gigahertz masers are brightest and the shell appears to be shrinking. So then I use domain units for the computer. So one domain unit has the full codex model on it, and the maser ring is at about 0.44 domain units. So the star size is 0.2, and that comes from estimates from WX Pusk. And I sort of acknowledge that the radio photosphere may be larger than the optical value. Okay, so the geometry of these things looks a bit like this. Ugh. So you've got your cloud there, the blue things, and the star is the big red thing. So can you say anything about the velocity difference between these clouds? So the Doppler velocity is not all that big. So if you take just the sort of notional centers of these clouds, can you actually say whether they're velocity isolated or not? And the answer is, if I go forward a couple of these slides, so these are the codex models, sort of plotted the whole of a cycle on here. So this curve here is the one that I'm using, and so they're all contracting, which is sort of what you expect. The velocities are negative, radial velocities, and so the centers of these clouds are going to be sort of a couple of kilometers a second negative. So if I go back to here, so if you just took the velocities of the centers, they'd be isolated. But if you include a velocity gradient from the codex model actually within the cloud, then you can get an internal shift of up to about plus or minus 6.5 kilometers per second for the central value. So you could have some radial velocity zero somewhere, and you can get possible good zero shift lines of sight for perhaps a few places within the clouds. So how probable are the overlaps, and why are they possibly important? Well, They're important because they're the only things really that can get rid of a bright object in front of the star, because you would have to have some saturating beam going across in front of the star in order to steal most of the inversion and make the emission coming from in front of the star very weak. And if you don't have those overlaps, then the brightness of the star being so much more than the rest of the background would tend to give you bright objects over the front of the star, which is not what you see. So theory of the overlap, so I've used something that was done for megamasers, in fact, but it gives a Poissonian probability if the filling factor is low. It has a modified upper limit for the number of objects, and the probabilities of getting two clouds in your line of sight for means of 1, 0.5 and 0.2, which is probably about the right range, come out to be 0.18, 0.07, 0.016. So not all that common. And there's also a function for the mean gain, but it's not incredibly useful without running the computer, because we don't really know what this function here is when the maser is saturated. So yeah, so I should just mention, if you look at the solid black and the solid green, they're one cycle apart, right? One period apart. So the model doesn't in fact reproduce the same conditions for every stellar cycle. So it perhaps reflects the real objects in that respect. So the clouds get irradiated by a background from the star, which has that intensity relative to the saturation intensity. So it's just over 10 to the minus 4 times T in units of 1000 K. The dust has that opacity, that wavelength dependence, and it's quite optically thin, about 10 to the minus 2 at 43 gigahertz. And so you have the CMB, which is modified by dust from the rest of the solid angle, converging on each node of the domain cloud. And there's the point, I guess, is a big contrast between the bright stellar rays and the weaker background rays. So if we say that these objects that form the masers are pseudo-spherical clouds, then if you put no velocity gradient inside the cloud, the result that you get is very sort of counter to observations. So you get a bright maser, you get a bright clump of masers in front of the star, and with the star here, the cloud here, you get much weaker emission, right? So basically the bright stellar background is getting amplified even through saturation and giving you much brighter objects in front of the star than in the ring. Okay. So if you were looking with limited dynamic range of something like 1000, you'd sort of see the yellow bits here and not much else, which is not as observed. And if I put in the full codex radial velocity gradient inside the cloud, they get a bit fainter, generally. Again, you see mostly emission in front of the star. There's some sort of tiny little bright spots, tangentially amplified through sort of lucky, very low velocity shift line of sight chances. So the spectrum here is brighter. So on the flux density scale, so it's done in these sort of scaled units. So the star would have a flux density of a few times 10 to the minus 11 on those units. And so this is brighter, but on the other hand, if you packed in a lot of these objects, maybe you'd just about get enough to get up to the same sort of flux density, but probably not. So it looks like spheres are not a good model, at least if they are dilute, right? So, or have a low filling factor. And if they have a high filling factor, it's much more like the prolate objects that I'll come to shortly. So if you try then flattened clouds instead, so we're now sort of trying things that are sort of tangential to or sort of parallel to the stellar surface, that, as you might expect, if they were flattened by radial shocks, then you still get a bit of material emitting in front of the star, but you now get much brighter objects in the ring. Okay, so with that view, you could, if you had quite a lot of objects like this round your ring, get a brighter ring emission than the emission from in front of the star. So this could do it. So shock flattened clouds is certainly one model that might work. So this is just a bit more about this idea of this weak background from the CMB and dust. But you've got maybe a long path and the bright background from the star with a shorter path. Which one wins the race to saturation? And the answer is, well, you need this gamma I1 minus I2, so gamma times the difference in these lengths, which is a sort of Maser optical depth. Naively would have to be about 6.6. And I would say it's actually what you need from the computational models is considerably less than that, but two is not enough. Okay, so a single overlap of a spherical cloud won't do it. And there is considerable complication from density and velocity gradients. Okay, so if I put that same sort of cloud in, but I now put the internal velocity gradient from the Codex model inside the cloud, it gets even better. So you now get some brighter emission still in the ring, and it doesn't do an awful lot to the emission in front of the star. Now you can do even better if you go to a prolate sort of object, but then the arrangement is quite different. So the only way to have something that still keeps the symmetry is to sort of have your star and then some rather random magnetic loops, perhaps. The moment you put in an organized magnetic field, then it becomes a lot more complex to consider because of the asymmetry then imposed by the magnetic poles. So you now get, if you put the prolate cloud just in front of the star, sort of like that, it's very weak, you can barely see it, but it gives you a very nice bright object in the ring if the prolate cloud is actually pointing at you. So it's better than the oblate clouds if the direction's right, but there would be implications for polarization then, because in this case you would always expect a signature corresponding to the field either towards or away from you, pretty much. How am I doing for time? Okay. So those are the conclusions then. So pseudospherical clouds with a minimal internal velocity gradient produce just too much intensity in front of the star. And I think that's a fairly strong result. The flattened clouds are much better. Prolate clouds better still, as long as the field is not well organized. And if you have something that's like a dipole field or a solar field, you then have to consider the direction of observation relative to the magnetic axis and so on. Polarization signatures could possibly distinguish between the oblate and prolate models, because like say the prolate would have to be either towards or away from you, whereas the oblate cloud could give you fields that were sort of towards or in the plane of the sky, so you could see different polarization signatures. Right, thanks.
Thank you, Malcolm. Are there any questions about all the masers that we've seen over the past 15 minutes? No. Right, yeah, Thaisa.
Hi, Malcolm. I'm wondering if it's possible to use your model to discover new masers to observe, to predict that whatever transition could be masing.
Do you mean just for SiO or in general other molecules?
Either, both.
Yeah, maybe. If you've got all the information about the Einstein values and the collision cross sections and all that for a suitable number of levels, then yeah, possibly.
Is it the sort of thing where if we know that we have a few masers in one source, we should look for some other specific masers, for example, or is that a bit too mysterious?
Sorry, can you say that last one again?
So if we have some observations of masers towards a particular star,
yeah,
could your model predict other masers that we might also be able to detect?
I mean, yeah, if you sort of knew what the chemical distribution was or some reasonable estimate of it, yeah, could give it a go.
Interesting, thanks.
All right. Are there any further questions? Oh, yes.
Thank you. The SiO masers, sorry, you were speaking are in the V equal 1, V equal 2. Is that right? So in the vibrationally excited states?
Yeah, so I think that the ring structure that I sort of showed in probably the second slide, it's for the sort of low J and low V states. The higher one, so certainly if you go to sort of J is 5 to 4, 6 to 5, like in the atomium observations with ALMA, you see very different distributions. They don't look like rings necessarily.
Okay, and the question was, whether the SiO in the J1 to 0 in the V equals 0 shows maser emission or not, because I have some observations that show some strange asymmetries in the line profiles that could be maser, but as far as I know, the main masers are in the vibrational excited states, not in the V equals 0.
Yeah, I think in a lot of objects, V equals 0 is well modeled by thermal emission.
Okay.
Maybe with occasional little maser spikes on top of it, but it doesn't often maze.
Okay.